Hello and welcome back to Basic Topology, the video series where we talk about topological spaces and what we can do with them in analysis. And indeed, in today's part 8, we will talk about some very important spaces in applications, namely so-called locally compact Hausdorff spaces. And since we already know what Hausdorff spaces are, now we have to discuss what locally compact means. However, before we go into the definition, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with a membership on Steady or Patreon, you can access a lot of additional material for the videos. For example, I have books, PDF versions and quizzes to download. Okay, then let's go to the notion locally compact, which might already be self-explanatory. And to see that, let's first recall the attribute compact, which makes sense for subsets in a topological space. This means a given subset of X is either compact or not compact. Hence, the whole topological space X as a subset can also be compact depending on the topological space. Obviously, these would be very special topological spaces, but anyway, we can look at some examples. Indeed, by looking at the standard topology on the real number line, we already see a lot. So for example, we could take the topological space given by the unit interval with the standard topology. So please recall, this is the topology induced by the absolute value as a metric on the unit interval. So in fact, just the standard way to define open sets of the unit interval. However, in that case, X as the unit interval is an open set with respect to this topology. This is always important, the whole space is always an open set. But moreover, the whole space is also a compact set here. Hence, in that case, we actually have a compact topological space. So in that sense, we have a very special topological space, which is usually not the case. So for example, if we take the whole real number line together with the standard topology, then R is definitely not a compact set. Hence, this one is not a compact topological space. However, if we take a different topology on R, this can still happen. For example, the trivial topology, which we call the indiscrete topology, will do it. There we only have two open sets, and for this reason, every subset of R is compact. Hence, here the whole space is a compact topological space. And as you can see, this is a strong requirement, something we would call globally compact. And now in the next step, we want to weaken this requirement and just talk about locally compact topological spaces. So the question here is, what does it mean that the space itself is locally compact? And indeed, the key ingredient here is that we need the neighborhood notion to define a property locally. So roughly speaking, a topological space Xt is called locally compact if it has enough compact neighborhoods. So this means no matter which point X we take, we always find a neighborhood of X that is compact. So there please recall, a subset is called a neighborhood of X if it contains an open set that also contains X. So in the picture, this is quite simple. Just consider a topological space capital X, and then we can just take any element X from it. And for this X, we find a whole neighborhood that is also compact. This simply means that this compact set contains a whole open set that also has X as an element. Therefore, in a locally compact topological space, the neighborhood around a point X can always be described by a compact set. And indeed, this is a big advantage for every property we want to describe locally, because there we can use the compactness. And moreover, you might already know the most important example, namely the real number line here with the standard topology. Or more generally, we can also go to Rn with the standard topology. So there you should know that the Euclidean norm on Rn defines the standard topology on it. And as before, this is not a compact topological space, but a locally compact one. And this is quite easy to see because we have our epsilon balls in Rn. So more precisely, we have a ball that is centered at the point x and has radius epsilon. And the common notation we have is b epsilon of x. And for the sake of completeness, let's write down the definition. So we have all the points y in Rn that have distance less than epsilon from x. So we have x minus y in the Euclidean norm, and this should be less than epsilon. And for epsilon greater 0, this is definitely an open neighborhood of x. And now we can make it to a closed set by using the closure of this set. So this one is definitely a closed and bounded set, which means we can use the Heine-Borel theorem, which simply tells us that in Rn, closed and bounded sets are exactly the compact sets. This works in Rn with the standard topology, so here we have our compact neighborhoods. So in fact, the standard topological space we have here is actually what we want to generalize. Since it's also a Hausdorff space, it brings us to the concept of a locally compact Hausdorff space. Which means we have two important ingredients here. On the one hand, we can always separate 2 points. And on the other hand, for each point we can even find a compact neighborhood. And now the thing is that every metric space is a nice Hausdorff space, but in general not locally compact. So in that sense, we don't completely generalize the concept of a metric space with a locally compact Hausdorff space. However, we want that notion for applications because a lot of properties or analytical notions are defined in a local sense. So for example, continuity at a point or differentiability at a point are always defined just in a neighborhood around this point x. And then it's really helpful to always have compact neighborhoods to define these notions. So I would say it's always good to have a vector space with a topology in mind like Rn. So for example, you could always consider a real or complex vector space together with a norm, and you know this norm induces a topology. Hence, in such a vector space, all our topological notions make sense. However, such an abstract vector space might not be so different from Rn because we can see it's only locally compact if it's finite dimensional. So there you already see, for general vector spaces, the concept of being locally compact in Hausdorff is very restrictive. Therefore, we will not just consider locally compact Hausdorff spaces, but still, these spaces are important for a generalization of Rn. For example, we will see that in the next videos when we talk about continuous functions. So I really hope I meet you there again and have a nice day. Bye bye.